and I'll be presenting on privacy-preserving datasets of eye tracking samples. Re-identification from public datasets is not a new privacy risk. A seminal example of this is the research by LaTanya Sweeney in 1997 that showed how the then governor of Massachusetts could be re-identified. This resulted in his medical prescriptions being leaked to the public. We consider VR eye tracking data in our work and use two datasets as a motivating example. The datasets include age and gender. If age and gender were anonymized in the way recommended by Sweeney, the datasets would have been k-anonymous. This is a guarantee that re-identification risk is 1 over k or lower. Sweeney recommended grouping age and gender values into ranges, which prevents unique combinations from singling out individuals. However, the datasets considered here also include raw eye tracking data. An attacker can use this data to train a model to re-identify each participant. We computed the success rate of a re-identification attack if we protect just age and gender with k-anonymity, and if we also apply k-anonymity to the eye tracking data as well. The result that you can see here is the attack success rate, or the percentage of individuals correctly identified as a function of the privacy parameter k. If we only protect age and gender, the tall bars with lines show attack rates above 80%. If we also apply k-anonymity to the gaze data, we get the expected result, falling under 1 over k. Thus, we see that if we want to enforce privacy guarantees for VR datasets, we have to also consider gaze data. There's active work in formal privacy for eye tracking datasets in recent years. The existing mechanisms vary by privacy guarantee and data type. The majority apply for datasets of typical eye tracking statistics as features, such as blink rate or frequency of fixations in saccades. The only work that considers formal guarantees for gaze samples is by Lee et al. Called Kaleido. While feature datasets are useful for modeling in applications such as activity recognition, gaze samples simply enable more applications. Our contribution relative to this work is bringing the guarantees of k-anonymity and k-gamma plausible deniability to gaze samples. Previously, at VR 2021, we presented mechanisms for samples that ran in real time to reduce re-identification risk in the context of streaming applications. However, these mechanisms did not have formal privacy guarantees attached to them. In this work, we still target gaze samples, but instead focus on datasets. The mechanisms we propose require event detection, similar to the past work, which had used events for specific applications, but here, events are used to synthesize data with a process that must be run offline. Datasets can still be used to support foveated rendering by training gaze prediction models. The Kaleido mechanism spans both of these scopes. The mechanism can run in real time or be applied to datasets. Thus, we compare our two novel mechanisms based on synthetic data to the differentially private noise approach of Kaleido. Differential privacy for spatial data adds noise to cloak the real gaze position. DP is very well known in different contexts, but also has a known negative impact on utility in those contexts. More details on this can be found in our paper. K-anonymity is achieved by grouping and averaging data parameters used to synthesize new gaze data. In a more simple example, let's say we start with 6 unique data points as these triangles here. If k is set to 3, we cluster the data points into 2 groups of 3. And then we simply average them together. The final release data is k copies of the average from each grouping. However, if you're using this dataset for research, you might not be very happy to receive duplicate data just to satisfy a privacy guarantee. On the other hand, plausible deniability generates synthetic data instead of averaging existing data. The definition says that it is plausible for at least k real data points to have generated any released synthetic data. Looking at this visually, we have a generative model that we train on all identities in a dataset. We then use this model to generate new synthetic data, y. This data y is then compared back to the original data to ensure that it has k plausible seeds. This is a privacy test, achieving a guarantee on the risk of re-identification. We evaluated our privacy mechanisms for applications in gaze prediction and activity classification. dgaze trains a model to predict future gaze positions, which can be used to beat latency in foveated rendering. EHtask trains a classifier for activity type, such as whether the user was performing visual search, previewing, or tracking a specific object when viewing a 360-degree video. I refer you to the paper supplementary for pseudocode of how to implement these mechanisms. Ours are at k-same-synth and event-synth PD. All mechanisms reduce identification rates of the datasets, with lower numbers indicating higher privacy. We also computed the runtimes across these mechanisms, and all methods were quick enough to be practical when considering up to 15 hours of gaze data in one dataset. Kaleido had the lowest re-identification rate for each task at a high level of privacy for the parameters we examined. But as you'll see in the next slide, this low re-identification rate comes with some very significant compromises to utility. So here, we visualize gaze data from each method. The blue dots are the original gaze positions, while red dots are from the synthetically generated data. The lowest privacy parameters for each mechanism are shown in the leftmost column, with the highest level of privacy parameters on the right. So we can see the effect as level of privacy increases for each mechanism from left to right. For k-anonymity, the data points roughly overlap, with small differences introduced at higher k values. The PD method in the middle row retained the original distribution most closely, introducing some noise that does trail off from the original data. The DP mechanism on the bottom row introduces the most noise, which is what we had expected. And while we see a good amount of overlap here on the left, with higher privacy, the spatial noise increases, scattering away from the original data. And at the highest privacy level, we see a sparse sampling that diverges from the original data completely. So while the re-identification rate was reduced the most, the eye tracking data is no longer usable. The main takeaway from our work is that the recommended mechanism depends on the application you're going for. Past work on feature data had found a practical trade-off for a k-same mechanism. For samples, if the data will be used to train models for gaze prediction, k-same-synth is recommended to retain utility in the trained model. This application is not possible with only feature data, and our result introduced only 2.2 degrees of error, which could be accounted for in the context of foveated rendering. We describe this further in section 5.3 of the paper. If the goal is to train activity recognition models, it is best to go with event-synth PD, as it retains utility and visually matches real data, as shown in section 5.2. A practical trade-off was also found for the Kaleido mechanism. However, this result came from the reduced temporal sampling rate of the output noisy data. And in this case, the model is able to leverage head movement data as well to maintain classification rates. So our finding for DP may not apply when gaze data is the only input to an activity recognition model. Thus, we recommend event-synth PD in this case. Future work includes more mechanisms for sample datasets to achieve better utility, which includes better generative models for plausible deniability. Considering formal guarantees for other forms of sample data in XR, including head and hand motions, which have been shown to be highly identifiable, is also part of our future work. The scope of this work allowed us to collect and process the entire dataset offline to reach the guarantee. However, an exciting challenge would be to explore alternative formal guarantees for real-time data, including social VR and gesture input systems. And last, the definition of privacy we considered for our datasets was based on identification. However, additional privacy risks can arise when considering what users look at, which provide insights into human behavior that can reveal gender, sexuality, or personal interest that could be harvested for personalized ads or for bias and discrimination. And that will wrap things up. Thank you for our time, and please read the paper and check out our project websites for more details and pseudocode of the methods. Thank you.